Hello guys, welcome to class. How are you doing today? This is Miss Adana Ogu, and today we'll be taking a topic in chemistry. So far so good. We've treated topics for week 1 to week 6. So in this particular class, we'll be looking at week 7 topic. I hope you've been copying your notes and you've been doing the assignment. So our topic for this week is saturated hydrocarbons. Then our focus is majorly on alkanes. Now in last class we talked about saturation in hydrocarbon and other terminologies that we discussed. I hope you watched the video 2 or 3 times so that you can get a better understanding of it. Please always endeavor to play the videos back 1 or 2 times so that you get a better understanding, and also ask your question wherever you need clarification from. So let's look at our learning objective. At the end of the class, you should be able to define saturation in hydrocarbon and give examples, write the general molecular formula of the alkanes, state the first 10 members of the alkanes with their molecular formula, state physical and chemical properties and the uses of alkanes, understand the rules that govern the writing and naming of organic compound, and write and name simple hydrocarbons. These are the learning objectives, the things you are to achieve or have known at the end of this class. So let's go into the topic, saturated hydrocarbon. So like we discussed last time, when we said saturation in hydrocarbon or in organic compound, it means that in that particular compound or in that particular organic compound, all the bonds are single bonds. But in a case where you have double or triple bonds, we call that unsaturated compound. So saturation in hydrocarbon means that all the 4 bonds of carbon are single bonds, meaning that all the 4 bonds of carbon are attached to carbon. They are either to carbon-carbon or carbon to hydrogen. They are all single bonds. Now look at these examples that you have here. You have ethane, propane, and the rest of them. Look at it. You have each of these carbon bonded to single bond, then this single bond. Now I told you that each carbon can attach to 4, that can only form 4 bonds. So in each case you have 4 bonds and they are all single bonds. Now if you take a look at this is a cyclo chain, and these are this is cyclohexane because you have 6 carbon atoms. So if you count the bonds for each carbon, you have 1, 2, 3, 4. So for each carbon in this cyclo chain, you have 4 bonds that are single bonds. So this is known as saturation in hydrocarbons. So what I'm saying in essence is that saturated hydrocarbons are the alkanes and the cycloalkanes. Those are the saturated hydrocarbons that exist, the alkanes and the cycloalkanes. So let's look at the alkanes proper. Now, the alkanes are saturated aliphatic hydrocarbons. Now, when we say saturated, I explained that's just a short one. The aliphatic means they are hydrocarbons which are under the group of alkanes, alkenes, alkynes, and the cycloalkanes. So, alkanes are aliphatic and they form the homologous series with general molecular formula CnH2n+. So remember in our last class we talked about homologous series. I said that all homologous series follow a general molecular formula. So in this case you have the general molecular formula of the alkanes to be CnH2n+2. Now the first 5 members and their molecular formula is as follows. You have methane with carbon 1. So you have 1 times 2. 2 plus 2, 4. That's why the molecular formula is CH4. Then ethane, carbon 2. 2 times 2, 4 plus 2, you have 6. That's why the molecular formula is C2H6. Propane, 3 carbon atom, 3 times 2, 6 plus 2, 8. That's why the molecular formula is C3H8. All the way to pentane that we have here. Then your note, you have up to 10. And even beyond that, you can actually get the molecular formula when you know the number of carbon atoms for the alkane. So the general molecular formula, if you follow the general molecular formula, CnH2n plus 2. Then next, let's look at the properties of alkanes. Now, the first 4 members are gases, the next 6 members are liquid, while the higher members are soft solid. Remember in our last class, I told you that homologous series, they usually follow a general molecular formula, which we said just a while ago, and then there is a little graduation in physical properties. So there's as you move down the group of the homologous series, there's a little change, graduation in their physical properties. That's why the first 4 members of the alkanes are gases, next 6 are liquid, then the higher members are soft solid. Then another thing is that their boiling point increases as you move down the group, physical property. Then generally the alkanes have no action on litmus paper, that is, they are neutral substances, neutral compound. Then, since all the 4 valence electrons of the carbon in the alkanes have been used up, they are very stable compound. They are stable and they are chemically not very reactive. So, because all of them are saturated, single bond, they have been used up, so the compounds are chemically not very reactive. Now, like we said, if you know the characteristics or the property of one of the homologous series, you can actually know or be able to predict the property or the characteristics of other members. So let's look at the first member of the alkane series, which is methane. Methane is structurally written as C carbon bonded to 4 hydrogen atoms, and the molecular formula is CH4. So now methane itself is a major component of natural gas and also a component or a constituent of petrol. So the major component of natural gas is methane, and you can find it with mixture of other compounds in petrol or even coal. Then it's often referred to as marsh gas because it's given up naturally in swamp and marshy areas. Then also is a major constituent of fire damp. Now, fire damp is a place in coal mines where methane is majorly found, and because of insufficient oxygen, if that place is poorly ventilated, it causes explosion. So most times that place is dreaded because of the explosion that occurs in coal mines. Now, next thing we are looking at is the laboratory preparation of methane. Like I said a while ago, when you know the property of one, you can detect the property of other members of the homologous series. So, laboratory in the lab, methane can be prepared by the action of soda lime or sodium ethanoate. Now, sodium ethanoate is CH3COONA. Now, when you react it with soda lime, now sodium hydroxide, that is NaOH, is gotten from soda lime. When you react it, you have your product, methane. Now, see the setup. This is the setup of the laboratory preparation of methane. This is how the setup is like. Now, let's for other members, since we understand the laboratory preparation of methane, you can actually predict how other members of the alkanes can be formed. For example, let's consider this. You have, using an appropriate alkanoate, you can get other members. So if you have C2H5COONA reacting with sodium hydroxide from soda lime, you have ethane. Notice something here. Let's go back to the other one. Notice something here. You have CH3. So the hydrogen from this hydroxide gets attached to this CH3 and you have your products. So coming back to the next, the other members, you have C2H5 For example, you want to get ethane, so ethane, you have C2H5. So the hydrogen from the sodium hydroxide gets attached to it and you have ethane. The same thing, propane, C3H7, because the molecular formula of propane is C3H8. So you use C3H7COONA. For pentane, you want to get pentane with molecular formula C5H12. So you use a substance of C5H11COONA, the alkanoate with that molecular formula. Then, if for example, butane, which is C4H10, so you are going to use an alkanoate of molecular formula C4H9COONA. We add it to sodium hydroxide and you get butane. So I hope you understand this. So the properties of methane, let's look at the properties of methane. Methane is a colorless and odorless gas which is slightly soluble in water. Now, remember when we were talking about the general properties of alkane, we said that they are insoluble in water. So methane is slightly soluble in water. I mean, the alkanes are slightly soluble in water. Then it is less dense than air. Methane is less dense than air. Methane bonds in air or oxygen to produce carbon 4 oxide and steam. Now, that's one property. So, in fact, all organic compounds or all carbon-containing compounds bond in excess oxygen to produce carbon 4 oxide. Now, but in limited supply of air, they will bond to give carbon 2 oxide, which is CO. So if you look at the equation, you have methane in oxygen give you CO2, but in limited supply of air, you have the product to be this. So in sufficient supply, you have CO2, while in limited supply, you have CO. The product of combustion of methane. Now, burning is also known as combustion. So combustion of methane in sufficient oxygen will give us carbon 4 oxide, while in limited oxygen will give us carbon 2 oxide. Now, let me explain this carbon 4 oxide and carbon 4 oxide and carbon 2 oxide. Carbon 4 oxide is, now, if you have a coal fire, the gas that is given off at the surface is carbon 4 oxide, but at the middle of the coal fire where there is insufficient air, the gas that is usually produced is carbon 2 oxide. So that's how these gases are formed. Where there is sufficient oxygen, carbon 2 oxide is formed. Where there is insufficient oxygen, carbon 2 oxide will be formed. So for now, another property of methane is that methane reacts with halogens in the presence of ultraviolet light or sunlight. Now, that's the function of ultraviolet light or sunlight is to act as a catalyst. So to yield halo compounds. So remember, the condition for this reaction to occur is the presence of ultraviolet light or sunlight. So you have, for each of them, you have methane plus chlorine. We give you first the product. Now, in each there's substitution is a step-by-step process in which there is substitution of hydrogen atom in the alkanes by the halogen. Now, when we say halogen, chlorine, bromine, iodine. So when any of these iodine reacts with the with methane, so the carbon atoms in methane will be substituted with chlorine step by step. So in the first step, you have methane reacts with chlorine, you have hydrogen chloride gas, and then you have chloromethane. Then that chloromethane reacts with more of chlorine gas, and you have dichloromethane. Dichloromethane reacts with more of chlorine gas, you have trichloromethane, and then when trichloromethane reacts with more of chlorine gas, you now have tetrachloromethane. So subsequently, each of the hydrogen atom in methane is substituted by the chlorine atom. Now, the same thing can happen for the alkanes. I told you, if you understand the property of one, you understand the properties of other. So all alkanes react all alkane undergo similar reaction like methane. That is the only reaction that the alkanes undergo are combustion and substitution reaction. They don't undergo any other reaction. Combustion, that is burning of alkanes in air or oxygen. So in sufficient oxygen, you have carbon 4 oxide, while in insufficient oxygen, you have carbon 2. Then with the halogen, the condition for this to happen is ultraviolet light acting as a catalyst. So you have substitution of each of the hydrogen atom in that alkane with that halogen. So look at we use butane here as a case study. So you have the product of combustion for each of these. Then with the halogen, let's use bromine as an example now. You have the hydrogen in butane, one of the hydrogen is substituted with bromine, and you have bromobutane. Then again, bromobutane, sorry, going back to that. Now, bromobutane will now react with more bromine to give you dibromobutane. So the process continues until all of the hydrogen in butane is substituted for. So it's a step-by-step process. Next, we look at the uses of alkane. Now, alkanes are generally used as fuel, both industrially and domestically. So in the industry, you use them as fuel. For example, we said methane is the major constituent of natural gas and is used as fuel. Then propane is the constituent of our cooking gas. Propane and sometimes butane, cooking gas at home. Then the halogenated derivatives are useful in both chemical and pharmaceutical industries. For example, some are used as analgesic in medicine, while some are used to make insecticide and other things. Then they can be cracked to produce the alkanes, which are useful raw materials for many products. For example, ethene is used to make polyethylene. The polyethylene we use generally around us. So ethene, when hydrocarbons or alkanes, when alkanes are cracked, you can get those products. So those are the uses of the alkanes. Now, look at this image. You see the uses. You see methane, natural gas, propane, our cooking gas, butane, fine in lighter, majorly as fuel. So now, that's for that. Then we go to IUPAC Nomenclature. IUPAC means International Union of Pure and Applied Chemistry. It's a body that regulates the operation in chemistry. Now, IUPAC gives rule in naming of organic compounds. So when you say an organic compound, how do you know the proper name of this compound? So IUPAC have given rule. Number one is that the parent name is given to the longest continuous chain. Then and a group with one hydrogen less of the alkanes is referred to the alkyl groups. So for example, methyl is CH3. Remember, methane is CH4. So when it's one carbon less, it is called methyl CH3. Now that dash is showing you that it is attached to something. It will be attached to something. Then ethyl is C2H5 from methane. Now notice the name. The ANE in the alkanes is replaced with YL in the alkyl groups. Now, another rule is that give the smallest number to the location of all substitutes or branches. So you give the smallest number to all substitutes, to the branch or the location of all substitutes and branches. Then you can use prefixes like di, tri, tetra, when there are two or more substitutes of the same kind. Don't worry, we'll look at the example shortly. Then different substitutes on a parent chain are named alphabetically. So when they are of the same kind, you use di, tri, or tetra. But when they are of different kind, you name them alphabetically. So each name, now another rule you should know is that each name is written as a continuous name, no spaces, as a continuous name. Let's look at an example. Look at the first one. You have these chains of carbon. You have these chains of carbon. Now, you notice this is the substitute. This is the substitute. The substitute is this CH3. That's the substitute. So now you have this substitute attached, according to our numbering, is attached to carbon 4. Is attached to carbon 4. Is attached to carbon 4. Okay, good. So it's attached to carbon 4. Now look at it. How did I number it? Now I counted 1, 2. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7. So these are the carbon number of the carbon 1, 2, 3, 4, 5, 6, 7. Sorry, I have to correct that so that you can see the proper numbering in each carbon atom. So you see, good. So each of the numbers are on each carbon. So I counted 1, 2, 3, 4, 5, 6, 7. Now if you count, I counted from left to right. Now if I count from right to left, I have 1, 2, 3, 4. Do you notice the substitute is CH3? That substitute is on carbon 4, whether you count from left or from right. So the name of the carbon, now remember the first rule is that the parent name is given to the longest continuous chain. So you say heptane is the parent name, but before then you say 4 because the substitute is on carbon 4-methyl heptane. So that's the name of that compound. You see, it's a continuous name. There was no space between them. So you see, in that compound, the name is 4-methyl heptane because the parent chain is 7, longest continuous chain. Now, next one, for this next example, you have this. Sorry, please. There is rearrangements of the work based on the slide I'm using. So let me quickly correct that. So the proper thing is that the carbon must be attached to carbon, not anything else. Carbon to carbon, because the bond is between carbon and carbon. So I have this. Just a moment. Good. So look at this now. We have this. You are given this structure and you are asked to name it. So if you notice, we said that the rule is that you give the name to the longest continuous chain. So look at it. You have your numbering now will be, if you count from here, from left to right, you have 1, 2, 3, 4, 5. Are you following this? That's 5. Then you count from here 1, 2, 3, 4, 5 also. But notice, longest continuous chain. It might look like a branch, but this is a continuous chain. This here, you see this 1, 2, 3, 4, 5, 6 is the longest continuous chain. So this is the longest continuous chain. So your proper numbering is 1, 2, 3, 4, 5, 6. So you see that the substitute is on carbon 3. That's why the name is, and that substitute is CH3, methyl. So you have 3 methyl hexane. Hope you get that. So hexane because it's 6 carbon. Hexane because it's 6 carbon. So we have 3 methyl hexane. Now next, we look at the next one. Look at this. Sorry, there is a bit of rearrangement of these bonds because of this slide. So we have this. So we have this. So look at the numbers. One, two, three, 4, 5. Now, notice something here. Do you notice now? I counted from right to left. Why? Because according to the rule we said before, we said that you must give the location of the substitute the smallest number. So if I counted from right, from left now, you'll be 1, 2, 3, 4. Now this substitute is on carbon 4 and then 5, but the smallest number is 1, 2. Do you see? 2 is smaller than 4 and 3 is smaller than 5. So we counted from the right in this situation. So I have 1, 2, 3, 4, 5, 6. Now the parent chain is 6 carbon and the substitutes are on 2 different carbon on that chain. So I have 2, 3 showing the location of the substitute, and each of that substitute is a methyl group. So I have 2, 3 dimethyl hexane as the name. Remember I told you when there is 2 or more substitutes of the same kind, you use di, tri, or tetra. So we are using di because there are 2 substitutes of the same kind. So I have 2, 3 dimethyl hexane. Then now in this other one, this other example, like I said, there is a rearrangement of this work because of the system. So now look at this chain. In this chain, you have a group attached here, then here also. So you have that group attached there as well. So now the numbering, let's look at numbering. Now, so back to what I was saying. So you see this structure, if I counted from the right hand side, it will be 1, 2, 3, 4 on carbon 4. Then this methyl group will be on carbon 5. So compared to 1, 2, 3, 3 is smaller than 5. So you take this number. Now remember, we said that when there are 2 or more, 2 different groups, 2 different kind of group, you name them alphabetically. So I have now the name will be 4-ethyl because E in alphabetical order, E comes before M. So you have 4-ethyl, 3-methyl heptane. The parent name, parent chain is heptane, 7 carbon. And this group C2H3 is ethyl. Hope we get that. That's C2H5 group if you condense the formula. So that's the name of this compound. Now, next, let's take another look at another example. Another example, I have this. Write the structural formula of the following: 2,3-dimethylbutane. That's the name. So now, when you are giving a name and you are to name, giving the name of the molecular name or the IUPAC name of a compound, to name it, first of all, write the parent chain. So first you write at, since the parent name is butane, you write 4 carbon. But is 4. So we have 1, 2, 3, 4. So 4 chains, you write it down. Then you have 2,3-dimethyl. The substitute is a methyl group, CH3 group. So on carbon 2, so you count from left or right, I have 1, 2. So this is carbon 2. You put a methyl group, which is CH3. That's what you are seeing here. You see C bonded to 3 hydrogen. Then that carbon atom will only be able to take how many hydrogen now? 1. Why? Because you have 1 carbon. This is carbon. So in relative to this carbon, you have 1, 2, 3, 4 bonds. So the bonds are complete. So you can only take 1 hydrogen. Then remember, you have not completed other bonds. So now, in carbon 3, this is 1, 2, 3. On carbon 3, I'll put the other methyl group. So I have 1 hydrogen attached to it. Then you complete the other. So those other carbon without substitute, you complete it. So you have 1, 2, 3. So making the bond complete for this carbon, and then this carbon making the bond complete, you have 1, 2, 3. Hope we are following this. Then look at this other one. You can either do it this way or this way. So you can use this way. CH3. Now, first you write at the carbon chains. 4 carbon chains, you write it at. Then on carbon 2, you have CH3. On carbon 3, you have CH3. Now, the position, when I mean position, whether it is up or down, does not change anything. It could be up, down, or the way it is like this. So you have CH3, CH, then CH3. Now, why? 1, count the bond. I have 1, 2, 3, and then this hydrogen makes it the 4th bond. So in this one, you have 1, 2, 3, and that hydrogen makes it the 4th bond. So for this one, so you have carbon 1, then for each hydrogen 1, 2, 3. So plus this one making it 4. Hope I understand it. So that's the name of the structure of 2,2-dimethylbutane. The next one we are told to write the structure of 1,4-dibromocyclohexane. Now that's a cyclo chain, and it's a cyclo chain, and then you know cyclohexane, you put it in a circular form. So that's why I have the cycle 1, 2, 3, 4, 5, 6. So you write the 6 carbon in cycle in a closed ring. Then for each carbon, now we said 1, 4. So on carbon 1, take this as your carbon 1, you have the bromine atom. So you go to, since this is 1, so this is 2, 3, 4. So on carbon 4, you put the other bromine. So you complete the chain by completing the hydrogen. So on this carbon, I have 1, 2, 3 for bromine, then this makes it 4. So on this carbon, I have 1, 2, 3, 4. So complete them with hydrogen. Now this is 1, 2, 3, 4. 1, 2, 3, 4, and the rest of them like that. So you complete them for each of them. So when you are giving a name, you can actually write the structure of that compound that you are giving. So this is where we are going to end the class for today. I hope we actually understood what I've said. please and please, it's important you ask your question at this time. Anywhere you need clarification for, please ask me and I'll get back to you. It's very important to ask this question because this is the beginning part of this topic, and your understanding, these fundamentals are important for you to be able to deal with other words as we move on in our study in organic chemistry. So references of the updated notes for week 7 on your school's website are New School Chemistry by Ababio, Explicit Chemistry by Olaoye Oje, and then Essential Chemistry by Odesina IA. So please make sure you copy your note, and like I said, ask your question, and make sure, very importantly, you do the assignment as well. Thank you very much for listening. Till I come your way, keep staying safe, and God bless you. Bye. Bye-bye.